Okay, so finally, we can start to discuss vector diffusion map under the manifold model. So we need some discretization scheme because in practice we only have finite sample points from the manifold. So this is a sampling scheme. You have a vector field, a random vector. This random vector will map to to sample manifold. So we sample n points, xi, I from 1 to n, iid from random vector 1. So you get n points. Okay, so you sample n points from the manifold. Good. Now make some assumptions about the sampling process. Assume the induced probability measure is absolutely continuous. That can certainly be relaxed, but then we need more work. And because it's absolute continuous, by Radon-Nikodym, you can find a positive function, which is the density is a probability density function. And then we make another assumption saying that this density function is smooth enough, C4, and the inf is positive. Why do we need this condition? Because this inf condition assumes that we can sample everywhere without missing any piece of information. Otherwise, if there will be some region, some subset, such that the density function is 0, then this is equivalent to saying that we do not sample this region, or we are saying that the manifold we are sampling actually has some hole or some missing part. So the manifold topology will be different. So we make this assumption to guarantee that we can sample everywhere, we can fully understand the manifold in this sense. Now, this is R, this is P, not R. This is propriety, sorry. And this is the vector field. Okay, suppose I give a vector field defined on the manifold. Okay, can do a section, which is smooth. Okay, so now we have a sample. Good, we get a vector field. But so what? How to represent it? How to save it in computer? If you remember, vector field is abstract, and we need to save it in computer. How to do it? The solution is now we also sample the frame bundle. Over the frame bundle, at each point, we sample G1, G2, whatever you like. G1 is at x1, G2 is at x2, and so on. Okay, once you sample all these, once you sample the frame bundle, then you can save the vector field by evaluating the coordinate of the vector field at each point associated with the basis. So you save the coordinate of the vector field. And usually we save it as an n times d dimensional vector, which you can view as an n dimensional block vector, and each block is d dimensional vector. And this is a discretized vector field that is saved in the computer. So we have a way to represent a vector field on the manifold in our computer. Good. So with all this preparation, we can now run graph connection, generalize the graph connection Laplacian. And to generalize the graph connection Laplacian, just like before, we need several steps. First, you generate vertices. Those are all the sample points are vertices. And then you determine edges, E. Those are edges, just like what we did in diffusion maps before. And then we determine the weight. What is the weight? Weight is just a kernel function k, which you can imagine this is a kernel, this is Gaussian function, and you evaluate Euclidean distance, because in practice we do not have geodesic distance, we cannot access the manifold. So you use the ambient space distance to represent as a surrogate of the geodesic distance. And you have some weight, epsilon. Epsilon usually is a small number, which is usually understood as bandwidth. Okay, and this is the weight, which tells you that if this k is Gaussian, then if 2 points are far away, then this kernel value will be super small, which tells you that 2 far apart points will have a very small weight. But if 2 points are very, very close, even much closer than epsilon, square root of epsilon, then since K is Gaussian, then Wij will be large, which tells you the weight is large. Or we call this weight affinity. And then you build up connection by parallel transport. Now you have the parallel transport from Xi to Xj. But remember, parallel transport is also an abstract notion. So we cannot save it. So we need to use the frame bundle sample again, use GI inverse and the Gj. So then this guy becomes a D by D matrix. Okay, so we save Gij. And Gij describes how you move the vector from Xj to Xi. And in some applications, this guy Gij is given directly. But in some other applications, this is not given. Then we need to do the estimation. And this is given in the fourth lecture. Very good. Now, if we do a quick comparison with graph Laplacian, how do we get graph Laplacian? In a very special case that Gij is 1, and 1 is SO1, spatial orthogonal group of dimension 1, which is SO1. SO1 is just 1.1. In this case, suppose we set Gij in this case, then we get graph Laplacian, or just a random walk on the graph. This is a trivial reduced case, and if you use the bundle language, then we reduce to the trivial line bundle. And in general, if you have the vector bundle, vector field bundle, vector bundle, then tangent bundle, then you have the vector V, just like I told you, n times d-dimensional vector V, and if you evaluate D inverse S, which is the normalized transition matrix, and you evaluate at the ice block, then you can rewrite it in this way, just like in diffusion map. And this guy is the probability of jumping from J to I. And well, D and S, those are the scenes in the definition of vector diffusion map, which you can find in the previous lecture, or I think in the next slide we will recall it. And this guy tells you that is the probability of jumping from J to I. If you look at this guy. So in the end, this is saying that we have vector valued status of on the vertices, okay, and you want to do some random work. But when you do the random work, you respect the connection Gij. Okay, so that is pictorially what you have originally here, and now you have a vector field, vector valued status or field on the vertices, and how to compare or how to run the random work. You have from J, Vj, and you want to go to I, you just run Gij, apply Gij vector, parallel transport, and you get Gij, Vj, and you see Vj and the Gij, Vj can be very different. And now you compare them. You compare Vi and the Gij, Vj. That is what it means. So technically, everything we are doing is similar to what we did in diffusion map before, and we have discussed this probability jumping random work idea. But now we have one extra ingredient called Gij. That is, we want to respect the connection. Okay, and with all these quantities, finally we can construct the graph connection Laplacian. And the construction is technically almost the same as diffusion map. For example, we constructed an alpha-weighted kernel, alpha-weighted affinity, that is Wij divided by P epsilon alpha, and this P epsilon alpha is this guy. And if you take a look at this formula, it is very similar to kernel density estimation. So this is technically just kernel density estimation, and you do normalization of the density by weighted alpha. And then you construct the affinity matrix, which is called S. You have weight, and you have Gij, parallel transport, and you have the degree matrix, but you put I here. And then you have alpha normalized graph connection Laplacian is I minus D inverse S. And in the previous lecture, when we talk about general vector diffusion map, we just put everything. Yeah, so that is the setup. we have. And now we can put all together step by step and see what we have, what do we get. Okay, so if you have I minus d alpha inverse S alpha x bar, what is this x bar? If you remember in the previous slide, x bar is the discretized vector field that you save in a computer and you evaluate its i's block entry. Now you can just write it down directly, right? You know x bar, i's entry is g I inverse x. This is id x bar, this guy. And you have d alpha inverse S alpha x bar, that is this guy. And you evaluate on an i's block entry, so you get I here. So this is just a direct expansion. Now, we also expand this part. Remember we know Gij. Gij is Gi inverse P Gj. And you have x bar. Now we further write x bar. Remember, G bar x bar J is Gj inverse x. Now if you look at this formula, Gj inverse, you get cancelled out. That is, you recover the vector field. You recover the vector field. And then, once you have the vector field recovered, you have Gi inverse, which is linear, so you can move it out. Gi inverse, move everything out. And this calculation is what? This calculation becomes intrinsic. Now everything is in the vector field. Okay? So, what you get is this kind of discretization that we are familiar with before. The only difference is now this is a vector field, and once you have vector field, you need to respect the parallel transport. So you need to the connection, so you need to have parallel transport. But before, when we talk about diffusion map, because diffusion map is associated with trivial line bundle, so Pxi, Pxj is just 1, and f is a scalar. So before, you just get f of xi minus f of xj. That is in diffusion map. But in vector diffusion map, we have something more general, graph Laplacian. And you can show that all these terms will converge when n goes to infinite under my condition to this integral kernel. To this integral kernel. And this integral kernel is you have some normalized kernels, k alpha, k epsilon alpha, and the parallel transport x, and this is the density major, sampling density, and this is the Riemannian major. So asymptotically you can get this integral kernel asymptotically. And this integral kernel might remind you what we get in diffusion map. That is, in diffusion map, this kind of integral kernel will give us an approximation of Laplace Beltrami operator. And in graph connection Laplacian, in graph connection Laplacian, it will give us the connection Laplacian, which is second order derivative using the covariant derivative in a rough iterative. Okay, so finally, we can describe what we get asymptotically of graph Laplacian. And actually, graph connection Laplacian will converge asymptotically to connection Laplacian. Okay, so we have several results. The first one is the pointwise convergence of graph connection Laplacian to the connection graph connection Laplacian to connection Laplacian, and this is the result. D alpha inverse S alpha minus 1 epsilon x bar i's vector entry will give you all these quantities. And what are they? First, this is normalized graph connection Laplacian. We know that. This is the i's block entry, and you have some second absolute moments of the kernel, and this is the dimension. And if you remember, then you have a connection Laplacian, Laplace square, which I do not systematically introduce, but you can view it as a generalization of Laplace Beltrami operator to the vector bundle, and you can check it online with the background we introduced in the beginning of covariance derivative and so connection. You can get it easily. And now you have this kind of first order derivative term, where it disappears when alpha is 1, because when alpha is 1, this becomes a constant, so you get 0. So when alpha is 1, you just get pure connection Laplacian. And this Gi inverse, it is a coordinate evaluation. Remember, You just evaluate is a basis, and you evaluate coordinates of this vector. So you get a coordinate. This guy, this whole guy, GI inverse of the bracket, this is in d-dimensional, the d-dimensional vector. And if you do not put GI inverse, then you get this guy is in tangent space X. Okay, and this is bias, this is variance. So if you look at it, it is very, very similar to what we got in diffusion map, in graph Laplacian, and its relationship with Laplacian Chomsky operator. The only difference is now we respect the connection. And you can also approximate the heat kernel associated with the connection Laplacian. And that is for any time, the heat kernel associated with the connection Laplacian can be approximated in L2 by this guy. That is, you have T epsilon 1. This is the integral kernel we had before, and you raise power to T divided by epsilon. And that is what you have. When epsilon goes to 0, you get the heat kernel at time T in L2 sense. This result is kind of old. It is back in 2012. It doesn't have any convergence rate. So a new result will be announced in the near future. Okay, so that we have the rate, we know better, more quantification, and so on. We also have spectral convergence. So this guy is a discretization of the integral kernel I showed you. It is directly related to D inverse S. And the fixed time T, and if you denote the I is eigenvector and eigenfunction of this guy, or this is eigenvector of this guy as this and that, and the I is eigenvector and eigenvector field. Sorry, this is not eigenfunction, this is eigenvector field of heat kernel as these two guys. Then you can say that for any fixed I, you can find an epsilon n goes to 0, such that in probability you can get recovered eigenvalue and the eigenvector in L2 sense. And this can be generalized to, again, this doesn't have a rate, so we will have new results with rate and maybe even L infinity control and so on in the near future. Okay, and similar to diffusion map and the Laplacian Chomsky operator, we have uncertainty principle, which is a direct generalization of the notion that we encounter in signal processing about like high-dimensional business and so on. Because anyways, Laplacian Chomsky operator can be viewed as a second-order derivative over 0-1 interval, so you can view eigenfunctions as the Fourier modes and so on. And all these kind of notions are kind of similar. So whatever, once you have the Laplacian Chomsky operator, you have eigenvalue and so on. Eigenvalue always decreases. Sorry, this should be heat kernel. This should be heat kernel. Oh, sorry. I'm right. This is lambda. This is the connection Laplacian's eigenvalue, negative, and what I plot here is exponential to e lambda t. So this is heat kernel's eigenvalue, which is always less than 1. And you can say that when time increases, the higher order eigenvalues decreases and becomes smaller and smaller. So when time it becomes very, very long, you only see the first few eigenvectors remain. And the first few eigenvectors will give you the topological information. But when time is very, very small, then you get almost all eigenvectors preserved, and you see the geometry. And so, for example, you can see the topology, like Beatty number, using Wiesenberg identity for Hodge to get Hodge Laplacian, and that will be the connection, because the Hodge Laplacian and the connection Laplacian are related by Ricci curvature, and once you get the connection Laplacian, you can get Hodge Laplacian, and once you have the larger Hodge Laplacian, you can get Beatty number, and those are kind of more topological application of in data analysis is what we will discuss in the future. And the final few slides will be vector diffusion distance and geodesic distance. So if you remember, what is vector diffusion maps? Vector diffusion maps is that if we can try to define a new affinity between two samples. I consider the Hilbert-Schmidt of S tilde, which is the normalized affinity word connection of Laplacian. And if you do the expansion, that is what you have. And you can check it or see the previous lecture for some more details. And this suggests us to define vector diffusion map because of the symmetry. This is VLI, VRI, VLJ, VRJ, so we just split it and we define this guy, which is called vector diffusion map, so that the Hilbert-Schmitz norm will just be the inner product, which is a very nice structure, and that's vector diffusion map. And once you get to the vector diffusion map, you map your original data to a Euclidean space. And it also has a very special relationship with diffusion map, because anyways, as I said, diffusion map is a special case with a trivial Nye bundle. Okay, so get a trivial Nye bundle. In this case, diffusion map is a subset of vector diffusion map, because in this case, diffusion map is defined in this way, but vector diffusion map is defined in this way. So you can see that vector diffusion map is Vt, but you focus on lambda r is 1. Lambda 1 is 1. And then you change lambda I, and you recover diffusion. So in this sense, vector diffusion map is a superset of diffusion map. And it does give you some extra information and so on. And again, we'll talk about this issue from the principal bundle perspective in a later lecture. And now once we have the vector diffusion map, we can define vector diffusion distance as L2 distance after the mapping, like this guy. After you map, you evaluate their distance, which is called vector diffusion distance. And once you have vector diffusion distance, you can kind of apply different application algorithms. For example, you can run k-means to group images or something, just like what you want. And this is a theoretical guarantee of what vector diffusion distance behaves when you have a manifold set. And actually, it tells you that vector diffusion distance can recover geodesic distance local, only local. The theory says that if you have 2 points and their distance is actually very small, smaller than square root of the diffusion time, then the vector diffusion distance can give you this kind of approximation of vector diffusion distance with higher order error. And this is a picture you can see. You can see that locally it looks quite good, but globally it doesn't. And when time is very large, well, its behavior is not very clear at this moment. We still do not know what's going on when time is very large. But when time is small, the theory tells us that we can recover the local geodesic distance. And this is more examples. For example, very, very simple one-dimensional manifold, flat. And you see locally, you can see a very linear behavior which recovers the geodesic distance. But when time is very large, well, actually, we don't know what's going on. And this is the polar signal. Okay, so vector diffusion map is actually a tool that can helps us to recover the geodesic distance, the intrinsic distance. But why is it good? Why is it good? Because you can only recover local geodesic distance. You can say, hey, look, if I just use 2 points Euclidean distance difference, then we can also recover the geodesic distance locally. Why don't we use it? This is the key point. The key point is diffusion. And when noise exists, suppose you have 2 points A and B, okay? And you have several kind of points as the data. You want to move from compare A, B distance. Their Euclidean distance is the same as the Euclidean distance in between B and C. But if you look at this isthmus, now you will see that the geodesic distance, the diffusion distance that you diffuse from A to B is actually much more difficult than you diffuse from C to B. What tells you is, despite that, AB distance is the same as BC distance in the Euclidean setup. From the diffusion perspective, this distance is much smaller than this one. This distance, so this diffusion distance is much smaller than diffusion distance in between A and B. This allows us to say if we have 2 points, A and B, they are clean data points, but you have a lot of noisy observations, then diffusion difference can help you to tell the difference and to tell you that these 2 points are actually the same, but these two are different. So vector diffusion provides a robust way to determine the similarity. This is the similar to diffusion map and diffusion distance. And there are many more facts which I will not cover right now. For example, boundary can be considered. Just check the paper. And there are more general principle bundle structure is allowed, and we will talk about it in the future. Top eigenvector is the most parallel section that will be related to synchronization. We'll talk about it next lecture. And there are several other applications in future lectures. And those will what we will discuss. And there will be a bit more, one more slide, about spectral embedding, which is not directly related to data analysis at this point, but it has some kind of interesting behavior, saying that, well, we can better understand a set of manifolds in some way via spectral embedding. And this kind of spectral embedding business, well, we do have some results, but actually this result is still not fully connected back to application. So it's just an FYI in case you have interest, that can be discussed. But more work is needed. Yes, that is it.